Max Planck, often regarded as the father of quantum theory, was a German theoretical physicist who made a profound contribution to our understanding of the physical world. His work laid the foundation for quantum mechanics, a field of physics that would eventually revolutionize not only science but also technology. Born on the 23rd of April 1858 in Kiel, Germany, Planck's early education and career were marked by an intense passion for understanding the laws of nature. What set Planck apart was his ability to think outside the constraints of established scientific frameworks, which ultimately allowed him to pioneer a new way of understanding the universe. As a young man, Planck was deeply influenced by the rigorous intellectual climate of 19th-century Germany. His education in physics and mathematics led him to study the works of great physicists like Isaac Newton, James Clerk Maxwell, and Ludwig Boltzmann. These thinkers shaped Planck's approach to science, but it was his exposure to the emerging challenges within classical physics that would push him to develop his groundbreaking ideas. By the time Planck began his professional career in academia, many of the most fundamental principles of classical physics had been established. The laws of thermodynamics, which governed heat and energy, were understood, and the theory of electromagnetism, developed by Maxwell, had unified the understanding of light and electromagnetic waves. However, as scientists delved deeper into these laws, certain anomalies began to emerge, especially when they examined phenomena involving heat and radiation at the atomic scale. One of the most pressing problems in physics at the time was related to blackbody radiation. A blackbody is an object that absorbs all incoming radiation and, in turn, emits radiation based on its temperature. The problem arose when physicists tried to explain the spectrum of radiation emitted by a perfect black body. Classical physics, relying on Maxwell's equations and the laws of thermodynamics, predicted that as the temperature of a black body increased, the radiation intensity would continue to rise at higher frequencies, leading to an infinite amount of energy being radiated at short wavelengths, particularly in the ultraviolet region. This theoretical prediction was disastrous for classical physics, as it suggested that objects at high temperatures would radiate infinite amounts of energy, which obviously did not occur in reality. This paradox became known as the ultraviolet catastrophe. According to classical physics, as an object was heated, it would emit increasingly higher amounts of energy, and this energy would continue to increase without bound. However, experimental observations of blackbody radiation did not align with this prediction. Instead, experiments showed that the radiation emitted by a black body peaked at a certain frequency and then dropped off as the frequency increased. This experimental evidence suggested that the behavior of energy at very small scales was not in line with classical predictions, prompting scientists to rethink their understanding of how energy behaved at the atomic level. It was in response to this dilemma that Max Planck, in 1900, developed his revolutionary theory. Instead of accepting the classical notion of continuous energy emission, Planck proposed that energy was not emitted or absorbed in a continuous manner, but rather in discrete units, or quanta. He hypothesized that the energy of oscillators in a black body was quantized, meaning they could only take on certain discrete values, rather than any arbitrary value. Planck's bold hypothesis suggested that energy could only be emitted in packets, each with a fixed size, which he described using the formula **E equals HNIU**, where **E** is the energy of the quantum, **H** is a new constant, and **NIU** is the frequency of the radiation. This insight was not merely a mathematical trick. Planck's idea of quantized energy led to a new formulation of black-body radiation, which fit perfectly with experimental data. This equation, which became known as Planck's radiation law, explained the spectrum of radiation emitted by a black body in a way that classical physics could not. His theory resolved the ultraviolet catastrophe, showing that radiation intensity did not rise infinitely at high frequencies, but instead it followed a predictable curve that matched experimental observations. Despite the success of his formula, Planck himself was initially uncomfortable with the idea that energy was fundamentally quantized. He viewed the concept of quanta as a mathematical tool rather than a physical reality. For him, it was merely a way to solve a particular problem in physics. He did not fully realize that his work would lay the foundation for an entirely new branch of physics, quantum mechanics. His theory was, in many ways, a bridge between the classical worldview and the radically different approach that would emerge over the following decades. Planck's discovery, however, was only the first step in a much larger revolution. His work did not immediately change the way scientists thought about energy and matter. The idea that energy was quantized was so foreign to the established mindset that it took years for it to gain acceptance. However, this theory began to resonate with other scientists who were grappling with similar issues in their own work. In particular, Albert Einstein's work on the photoelectric effect, which demonstrated that light behaved as if it were composed of discrete particles, was directly influenced by Planck's quantization of energy. Einstein would later show that the concept of quanta could also be applied to light, further cementing Planck's legacy as the father of quantum theory. Planck's contribution to science was not just in formulating his radiation law, but in how it challenged the very foundations of physics. At the time, classical physics was grounded in a deterministic worldview where the universe operated like a giant clock, with every event determined by prior conditions. Planck's introduction of quantization broke from this classical tradition, suggesting that the behavior of energy at the atomic level was not continuous, but instead followed specific, discrete rules. This concept would go on to form the core of quantum mechanics, a theory that embraces the idea of probability and uncertainty, radically different from the predictable nature of classical mechanics. Planck's work had profound implications for the future of physics. Although he did not fully understand the broader implications of his discovery, he had unwittingly opened the door to a new and strange world of atomic and subatomic particles. It was a world governed by probability, uncertainty, and wave-particle duality, where particles could behave as both waves and particles depending on the circumstances. This new understanding would lead to the development of quantum mechanics, which would describe the behavior of particles at the smallest scales and lead to the invention of technologies that would forever change the world, from transistors and lasers to quantum computers. Despite the initial resistance from his peers, Planck's discovery set the stage for the work of other brilliant scientists, such as Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, who would expand on his ideas. Together, they developed the framework for quantum mechanics, which now stands as one of the most successful and fundamental theories in the history of science. Through their work, the once obscure and controversial idea of quantized energy became a cornerstone of modern physics. Max Planck's discovery marked the birth of quantum theory, and though he did not live to see the full implications of his work, his contribution remains one of the most profound in the history of science. His introduction of the concept of quantized energy changed the course of physics, leading to a deeper understanding of the nature of reality itself. Today, we recognize that Planck's discovery was not just a solution to a theoretical problem. It was the key that unlocked a whole new realm of science, one that continues to drive scientific progress and technological innovation. Max Planck's journey into the strange territory that would later be called quantum physics didn't end with the publication of his radiation law. The true weight of his discovery didn't fall on him immediately. He had solved a mathematical puzzle, yes, but he had also cracked open a door that revealed an entirely new architecture beneath nature's surface. The classical world, where energy flowed like smooth water, had suddenly fractured into steps, like a staircase too small for the naked eye to notice. Planck wrestled with this idea in silence, almost unwilling to acknowledge what it hinted at. The implications were too strange, too disruptive to the clean certainties of 19th-century physics. He had lived his entire scientific life guided by the belief that nature followed continuous laws, that the universe moved like the gears of a perfectly crafted clock. So, when his own calculations forced him to propose that energy behaved in time's jumps asterisk, he felt as though he were betraying the very foundations of physics. He often said later that he had been carried against his will into quantum theory. It is a deeply human thing, solving a problem only to realize that the solution contradicts everything you believed about the world. Planck faced exactly this conflict, a discovery that was undeniably correct, yet unsettling in its consequences. But while Planck hesitated to accept the philosophical implications, the universe didn't hesitate to reveal its secrets to those who were ready to look. Just a few years later, in 1905, Albert Einstein seized on Planck's quantum idea and used it with fearless clarity. Einstein proposed that light itself came in packets, later called photons. This wasn't just a bold use of Planck's work. It was a declaration that the quantum wasn't a mathematical trick, but a real feature of nature. If Planck had opened the door, Einstein walked through it and urged everyone else to follow. This was the moment when the world began to understand that Planck's discovery was not a patch on classical physics, but the first thread of an entirely new fabric. Once pulled, it began to unravel the old understanding of atoms, electrons, radiation, and even the structure of matter. Planck's constant asterisk, asterisk, H asterisk, asterisk soon appeared everywhere, like a signature written into the laws of nature. It showed up in Einstein's photoelectric effect, determining how electrons leap from metal when struck by light. It appeared in the Bohr model of the atom, dictating which electron orbits were allowed and which were forbidden. Later, it shaped Schrödinger's wave equation, Heisenberg's uncertainty principle, and the strange dance between probability and reality at the heart of quantum mechanics. Yet, while the world pushed forward, Planck himself stood calmly in the background, watching a new generation expand a theory he had accidentally birthed. He didn't try to claim ownership or reshape the discoveries of others. His personality wasn't one of showmanship or dramatic declarations. He was modest, disciplined, and almost stubbornly conservative in his thinking. And perhaps this is what makes his accidental revolution feel so remarkable. Quantum mechanics did not come from a scientist seeking to rewrite the universe. It came from a man simply trying to solve a small inconsistency in thermodynamics. But the universe, it seems, had other plans. As quantum theory evolved, the world grew stranger. Electrons seemed to exist in multiple states at once. Light behaved as both a particle and a wave. Observation itself changed the outcome of experiments. And in every one of these mysteries lay the quiet fingerprint of Planck's quantization. His constant, so small, so subtle, became the bridge between the seen world and the unseen one. It told physicists where the classical world ended and the quantum world began, marking a threshold beyond which intuition no longer applied. At first, Planck was uneasy watching the growth of this new physics. The philosophical implications troubled him. A universe governed by probabilities instead of certainties, a reality where particles did not have definite positions until measured. These ideas clashed with his lifelong belief that nature was orderly and deterministic. But Planck was also a scientist of discipline and intellectual honesty. He knew that physics must bow to empirical truth, even when the truth makes us uncomfortable. So he accepted the direction the younger physicists were taking, even if he never fully felt at home in the quantum vision of reality. Meanwhile, the scientific world began to realize the enormous power hidden in Planck's discovery. It wasn't just about understanding obscure radiation experiments anymore. Quantum theory was unlocking the structure of atoms. It was explaining chemical bonds, the periodic table, the behavior of metals, the properties of semiconductors, and eventually, the very mechanisms behind lasers, transistors, MRI machines, and the entire digital world. Quantum mechanics grew from a single strange idea into the foundation of the modern technological era. Every smartphone, every computer chip, every LED screen, every GPS device, every laser pointer owes its existence, in part, to the strange little constant that Max Planck introduced to fix an equation in 1900. What makes this story feel almost mythical is the contrast between the quiet father of quantum theory and the explosive revolution he set in motion. Planck worked with meticulous care, guided by logic and mathematics. He never aimed to overturn physics. Yet his discovery became the match that lit the fuse of the 20th century's greatest scientific leap. Physics before Planck and after Planck are two different worlds. Before him, nature was smooth, continuous, predictable. After him, reality shattered into quanta, tiny, indivisible packets that behaved unlike anything in classical science. The universe changed shape. As Planck grew older, he witnessed the full flowering of the quantum revolution, carried forward by Einstein, Bohr, Heisenberg, Schrödinger, Dirac, and many others. They built the strange cathedral of quantum mechanics, but the cornerstone was Planck's constant. Without it, the structure collapses. And throughout it all, Planck remained a figure of quiet dignity, respected, admired, and humble. He earned the Nobel Prize in 1918 for his discovery, but more importantly, he earned a place among the handful of scientists who reshaped humanity's understanding of reality at the deepest level. His life, however, was touched by great personal tragedy. He lived through wars, the rise and fall of empires, and immense suffering. He lost his children, endured political turmoil, and witnessed the corruption of academic life under totalitarian regimes. Yet through every hardship, he returned to science with the same calm dedication. For him, physics was more than a profession, it was a way to anchor the mind in times of chaos. The laws of nature, however strange and unpredictable they appeared in the quantum world, remained a source of meaning and stability for him. By the time Planck died in 1947, the world was already moving rapidly into the quantum age. Nuclear physics, quantum electrodynamics, and early transistor technology were emerging. The new era he had unknowingly launched was spreading through laboratories and universities across the globe. And today, more than a century after his radical proposal, we continue to peel back layers of the quantum realm he helped reveal. Quantum computing, quantum cryptography, quantum teleportation, these cutting-edge fields still trace their roots back to the moment Planck introduced the idea that energy comes in discrete packets. It is astonishing that such a tiny constant, asterisk 6.626 times 10 to the power of -34, could reshape the universe in our imagination. But that is the beauty of science. The smallest numbers can have the largest consequences. Planck's discovery was not loud or dramatic. It emerged quietly from a calculation, whispered its truth to those willing to listen, and slowly transformed everything we thought we knew about the cosmos. The universe, it seems, does not reveal its secrets all at once. It trusts them to those who observe with patience, humility, and daring imagination. Max Planck embodied all three. His discovery began as a reluctant adjustment to save classical physics, but instead became the spark that ignited quantum physics, a field that continues to evolve, surprise, and challenge our understanding of reality. The legacy of his discovery lives in every quantum equation, every modern device, and every new insight into the fundamental nature of existence. It is the quiet revolution that never stopped unfolding, and its echoes stretch into the far future of science. The problem of black-body radiation was one of the most perplexing challenges of 19th century physics, and it played a central role in the development of quantum theory. Black bodies, as defined by physicists, are objects that absorb all incident radiation, regardless of the frequency, and they are perfect emitters of radiation as well. This concept was crucial in understanding how objects radiated heat, particularly when heated to various temperatures. Theoretical models had been developed based on the laws of thermodynamics and classical physics, which predicted how these bodies would behave. Yet, despite the elegance of these classical predictions, they failed to account for the actual observations of radiation emitted by black bodies, especially at higher frequencies. The explanation for this discrepancy would not come from classical physics, but from a dramatic shift in scientific thought initiated by Max Planck. Classical physics, which was grounded in the laws of thermodynamics and the electromagnetic theory of radiation, was particularly adept at explaining the radiation emitted by black bodies at lower frequencies. However, when the temperature of a black body increased, classical theories predicted that the intensity of radiation would rise indefinitely as the frequency approached ultraviolet light. This prediction, however, was at odds with experimental observations. The radiation emitted by black bodies at higher frequencies, the ultraviolet range, did not continue to increase as predicted. Instead, the radiation plateaued and then began to decrease at very high frequencies. This discrepancy was problematic and posed a serious challenge to the validity of classical physics. The issue reached a critical point when, in the late 19th century, a well-known physicist named Lord Rayleigh, along with James Jeans, attempted to solve the problem mathematically. Their efforts resulted in what came to be known as the Rayleigh-Jeans law, which predicted that, as the frequency of radiation increased, the emitted energy would rise without bound, which led to the ultraviolet catastrophe. This catastrophe implied that objects such as heated solids would radiate infinite amounts of energy in the ultraviolet spectrum, which was physically nonsensical and was not supported by experimental results. The ultraviolet catastrophe cast doubt on the sufficiency of classical theory in explaining the behavior of radiation and the nature of energy at small scales. The stage was set for a major breakthrough. It was Max Planck who, in 1900, proposed a solution that would revolutionize the world of physics. Planck's discovery came when he was investigating the problem of black-body radiation and attempting to reconcile experimental data with the theoretical models of radiation. At that time, the problem seemed insurmountable using classical mechanics. However, Planck, driven by his desire to understand the behavior of heat and radiation, took a bold and unconventional step. He suggested that energy was not emitted or absorbed in a continuous manner, as classical theory suggested, but rather in discrete packets, or quanta. This suggestion was a radical departure from the continuous nature of energy that had been assumed in classical physics. It was this proposal, grounded in mathematical rigor, that marked the birth of quantum theory. Planck introduced a new approach to describe the emission of radiation by black bodies. He proposed that the oscillators inside the walls of a black body, which were responsible for emitting radiation, could only emit energy in discrete amounts, each corresponding to a specific frequency. The energy of each quantum was proportional to the frequency of the radiation, and this relationship was captured by a new constant that Planck introduced, asterisk, asterisk, h, asterisk, asterisk. This constant, now known as Planck's constant, became one of the most fundamental constants in physics, setting the scale for quantum phenomena. The equation asterisk asterisk E equals HNIU asterisk asterisk, where asterisk asterisk E asterisk asterisk is the energy of the quantum. Asterisk asterisk H asterisk asterisk is Planck's constant, and asterisk asterisk nu asterisk asterisk is the frequency of the radiation, provided the solution to the blackbody radiation problem. Planck's introduction of quantized energy levels immediately resolved the issue of the ultraviolet catastrophe, as it explained why radiation intensity did not increase indefinitely at higher frequencies. Instead, the intensity of radiation followed a predictable curve that matched experimental observations. This breakthrough had profound implications for the field of physics. Planck's work provided the first mathematical framework that could account for the observed behavior of radiation, and it marked the beginning of a new era in the understanding of energy and matter. While Planck's solution to the black-body radiation problem was a significant achievement, it was just the beginning of a deeper exploration into the nature of energy. Planck himself was not entirely convinced that his quantization of energy had any real physical significance. He saw it more as a mathematical tool that allowed him to reconcile theory with experiment. Planck did not fully grasp the larger implications of his discovery. He believed that the quantization of energy might only apply to black-body radiation and would not necessarily have broader applications. Despite this, his work laid the groundwork for future developments in quantum physics that would transform the field of physics. At the time of Planck's discovery, the concept of quantized energy was a difficult pill to swallow for many physicists. Classical physics had been so successful in explaining a wide range of phenomena that the idea of discrete energy levels seemed counterintuitive and even unnecessary. Planck's quantization was seen as a mathematical trick rather than a fundamental change in the nature of reality. However, over the next few years, other scientists began to see the potential of Planck's idea, and they started to apply it to other areas of physics. One of the most influential figures to build upon Planck's work was Albert Einstein. In 1905, Einstein used Planck's concept of quantized energy to explain the photoelectric effect, a phenomenon that classical physics could not account for. The photoelectric effect showed that when light of a certain frequency was shone onto a metal surface, it would eject electrons from the surface. Classical theory suggested that the energy of the ejected electrons should depend on the intensity of the light, but experiments showed that the energy of the electrons was dependent only on the frequency of the light, not its intensity. Einstein proposed that light itself was quantized and that it existed in discrete packets, which he called photons. This idea was directly influenced by Planck's work and led to the acceptance of the idea that energy could be quantized not only for heat radiation but also for light. Another physicist who built upon Planck's ideas was Niels Bohr. In 1913, Bohr introduced his model of the atom, in which electrons orbit the nucleus in discrete energy levels. Bohr's model explained why atoms emitted light at specific wavelengths and why the spectrum of hydrogen, for example, consisted of distinct lines rather than a continuous range. Bohr's work showed that energy levels in atoms were quantized, echoing Planck's earlier work on radiation. Bohr's model was a key step in the development of quantum mechanics. As the years went by, more and more scientists realized the power of Planck's quantum hypothesis. The development of quantum mechanics, which followed the work of Planck, Einstein, Bohr, and others, introduced a new way of thinking about the behavior of matter and energy at the atomic and subatomic levels. Quantum mechanics would go on to explain phenomena that classical physics could not, such as wave-particle duality, uncertainty, and superposition. It would lead to the development of groundbreaking technologies such as lasers, transistors, and quantum computers. Planck's work fundamentally changed the way scientists understood the nature of energy and matter. His idea of quantized energy levels, though initially met with skepticism, turned out to be one of the most important contributions to modern physics. His discovery solved a long-standing problem in black-body radiation and laid the foundation for the development of quantum mechanics. Planck's work demonstrated that the world of the very small at the atomic and subatomic level was governed by principles that were fundamentally different from the smooth, continuous laws of classical physics. Planck's quantum hypothesis was a spark that ignited a scientific revolution, one that would lead to a deeper understanding of the universe and drive technological advancements that continue to shape the modern world. Max Planck's introduction of energy quantization laid the foundation for quantum mechanics, but it wasn't until subsequent developments that the full scope and impact of his work became clear. The story of how his discovery transformed physics is incomplete without acknowledging the resistance and challenges that quantum theory faced as it emerged. Classical physics, with its well-established principles, was deeply ingrained in the scientific community, and the idea of energy existing in discrete packets seemed absurd to many at the time. Even Planck himself viewed his discovery more as a mathematical trick than a fundamental shift in our understanding of the physical world. However, as the consequences of quantization began to unfold, it became increasingly clear that Planck had opened the door to a new realm of physics, one that defied the expectations of classical mechanics. In the years following Planck's work, other scientists began to build on his ideas, creating a new framework for understanding the behavior of matter and energy at the atomic and subatomic levels. Albert Einstein, in 1905, applied Planck's concept of quantization to explain the photoelectric effect, where light striking a metal surface could cause the emission of electrons. Classical physics predicted that the energy of the emitted electrons would depend on the intensity of the light, but experiments showed that it depended solely on the frequency of the light. Einstein proposed that light itself must be quantized, existing in discrete packets of energy called photons. This was a direct extension of Planck's work, and Einstein's explanation of the photoelectric effect helped to further validate the idea that energy was quantized, not continuous. In 1913, Niels Bohr took Planck's concept of quantization into the realm of atomic structure. At the time, the nature of atomic energy levels was poorly understood. Electrons were thought to orbit the atomic nucleus, but classical physics couldn't explain why atoms emitted light at specific wavelengths when heated. Bohr proposed that electrons in atoms occupied discrete energy levels, and when an electron moved from one level to another, it emitted or absorbed energy in discrete amounts, exactly as Planck had proposed for radiation. Bohr's model of the atom, though imperfect, provided a significant step forward and demonstrated that the concept of quantized energy could explain the behavior of atoms. As quantum theory continued to develop, it became clear that Planck's ideas were not confined to blackbody radiation, but applied to all forms of energy. The quantization of energy was not just an ad hoc solution to a specific problem, it was a fundamental characteristic of nature. The theory of quantum mechanics was emerging as a comprehensive framework to explain the behavior of particles and waves at the atomic scale. This new framework was radically different from classical mechanics, which had been so successful in explaining macroscopic phenomena, but failed to account for the strange behaviors of particles at small scales. The development of quantum mechanics accelerated in the 1920 seconds, with scientists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac building on the work of Planck, Einstein, and Bohr. Heisenberg's uncertainty principle, Schrödinger's wave equation, and Dirac's relativistic quantum theory all contributed to the development of a more complete understanding of quantum mechanics. The uncertainty principle, for example, introduced the idea that there is a fundamental limit to how precisely we can know certain pairs of properties, like position and momentum, of a particle. This principle shattered the deterministic worldview of classical physics, where every particle's future behavior could be predicted with complete certainty. Schrödinger's wave mechanics, meanwhile, introduced the idea that particles could also exhibit wave-like properties. This was a profound shift in our understanding, as it suggested that particles, like electrons, could behave both as discrete particles and as waves, depending on the circumstances. This wave-particle duality became one of the defining features of quantum mechanics, and was later confirmed by experiments such as the double-slit experiment, which showed that particles like electrons could create interference patterns, a hallmark of wave behavior, when not observed directly. The development of quantum mechanics culminated in the mid-20th century with the establishment of the Standard Model of particle physics, which describes the fundamental particles and forces that make up the universe. The Standard Model, built on the principles of quantum mechanics, has been incredibly successful in explaining a wide range of phenomena, from the behavior of subatomic particles to the interactions between light and matter. It has led to groundbreaking discoveries in fields such as particle physics, condensed matter physics, and quantum computing. One of the most profound implications of Planck's work was its impact on our understanding of reality. Classical physics had painted a picture of a deterministic, predictable universe, where the behavior of all objects could be determined with complete accuracy, given enough information. Quantum mechanics, however, introduced a radically different view. It showed that at the atomic and subatomic levels, the universe is governed by probabilities, not certainties. Particles do not have definite positions or velocities until they are measured, and their behavior can only be described in terms of probabilities. This indeterminacy was a shocking departure from the deterministic view of the universe and challenged our deepest intuitions about the nature of reality. The philosophical implications of quantum mechanics have been the subject of much debate. The idea that the act of observation affects the outcome of an experiment, the so-called observer effect, has led to profound questions about the role of consciousness in the physical world. The famous thought experiment known as Schrödinger's cat, in which a cat in a sealed box is both alive and dead until observed, illustrates the paradoxical nature of quantum mechanics. This has led some to speculate about the deeper connections between quantum physics and the nature of consciousness, although these ideas remain speculative and controversial. In the 21st century, quantum mechanics continues to push the boundaries of our understanding of the universe. The development of quantum computing, which leverages the principles of superposition and entanglement, promises to revolutionize technology by solving problems that are currently intractable for classical computers. Quantum cryptography, which uses the principles of quantum mechanics to create unbreakable encryption, is already being used to secure sensitive information. The potential applications of quantum technology are vast, and we are only beginning to scratch the surface of what is possible. Max Planck's discovery, which began with his solution to the blackbody radiation problem, has had a profound and lasting impact on the way we understand the universe. His work was the spark that ignited the development of quantum mechanics, a theory that has since reshaped the landscape of modern physics. The transition from classical physics to quantum mechanics was not just a technical breakthrough, it was a paradigm shift that altered our very conception of reality. Today, Planck's constant is one of the most important quantities in all of physics, and his work continues to inspire new generations of scientists to explore the strange and fascinating world of quantum phenomena. Through the work of Planck and his successors, we have come to understand that the universe at its most fundamental level is governed by principles that defy our classical intuitions. The behavior of particles is governed by probabilities, and the world at the quantum level is inherently uncertain. This new view of reality has not only transformed our understanding of physics, but has also led to the development of technologies that are changing the world. Max Planck's discovery of energy quantization was the beginning of a journey that has taken us from the familiar world of classical mechanics to the strange and fascinating world of quantum physics. As we continue to explore this world, we are likely to uncover even more surprising and profound truths about the nature of the universe. Max Planck's role in the birth of quantum theory cannot be overstated. His work on blackbody radiation provided the initial insight that energy is not emitted or absorbed continuously, but rather in discrete units, or quanta. Planck's quantization of energy, although initially regarded as a mathematical convenience, would lay the foundation for a new understanding of the universe, one that would upend centuries of classical thought. While Planck's radiation law was a breakthrough in its own right, it was the implications of his discovery that set the stage for the development of quantum mechanics, a field that would soon challenge everything known about reality, the nature of light, and the fabric of the universe itself. Before Planck's work, scientists believed in the continuity of energy. Classical physics assumed that energy could vary in any amount, and that it followed predictable patterns based on established laws. But as scientists delved into the phenomena of radiation at very small scales, particularly in blackbody radiation, they encountered the infamous ultraviolet catastrophe, a paradox that classical physics could not resolve. The laws of classical thermodynamics predicted that an ideal black body, a perfect absorber and emitter of radiation, would emit increasingly infinite energy as the frequency of radiation increased, something that didn't match reality. Real-world experiments showed that black body radiation was much more complex, with intensity peaking at a certain frequency and then dropping off, a phenomenon that was ignored or misunderstood by classical theories. This discrepancy between theory and experiment created a gap in the understanding of the microscopic world, and it was this very gap that prompted Planck to step forward with a groundbreaking solution. To explain this anomaly, Planck proposed a radical idea. Rather than assuming that energy could be emitted in a continuous range, he suggested that it was emitted in discrete packets, each with a specific, quantized value. This insight was first applied to the oscillators of a black body, which were thought to emit radiation. Planck proposed that these oscillators could only emit energy in discrete amounts, proportional to the frequency of the radiation. This simple yet profound realization would forever change the landscape of physics. In doing so, Planck introduced a new constant into physics, **h**, known as Planck's constant, which would become one of the most fundamental constants in all of science. This constant, mathematically represented in the equation **E equals hn*u**, where **E** is energy h* is Planck's constant, and **NIU** is frequency, describe the size of each quantum of energy. The equation provided a precise mathematical model for how energy was emitted in discrete units, and it marked the birth of quantum theory. Although Planck himself did not fully appreciate the revolutionary nature of his discovery, his radiation law effectively resolved the ultraviolet catastrophe and fit experimental data perfectly. His work, though initially perceived as a solution to a specific problem, signified much more. The implications of his theory reached far beyond blackbody radiation and began to unravel a new understanding of the physical world. Energy was not continuous, but instead discrete, leading to the realization that the behavior of particles, energy, and light could not be fully explained by classical physics. Planck's work offered a glimpse into a new realm of physics, one that would question the very nature of reality, opening the door to a quantum world that would soon challenge the traditional laws of physics. At the time of his discovery, Planck's quantization idea was met with skepticism, even by Planck himself. He viewed the idea as merely a mathematical tool, a means to an end, rather than a fundamental truth about the universe. He was cautious about the idea of quantization, and he initially thought of it as a convenient hypothesis rather than a law of nature. But as other scientists built on his work, the quantum nature of energy would soon become a cornerstone of physics. It was Albert Einstein's work on the photoelectric effect, for which he was awarded the Nobel Prize in 1921, that first extended Planck's quantization concept to light. Einstein demonstrated that light, too, must be quantized, existing in discrete packets known as photons. The photoelectric effect revealed that light could not simply be thought of as a continuous wave, as previously thought, but as a collection of discrete particles that exhibited both wave-like and particle-like behaviors. Einstein's work, heavily influenced by Planck's concept of quantization, showed that energy was not just quantized in heat radiation, but also in light. His findings, coupled with Planck's radiation law, laid the groundwork for the dual nature of light, where it could behave as both a wave and a particle, depending on the situation. This duality would later be formalized in the development of quantum mechanics and would become a central theme in the study of quantum physics. The combination of Planck's insights on energy quantization and Einstein's application of these ideas to light fundamentally changed how scientists understood the behavior of light and energy. Despite his groundbreaking contribution to quantum theory, Planck's own views on the implications of his work were limited by the scientific knowledge of his time. Planck was committed to classical physics and resisted the more radical implications of his discovery. He viewed his quantization hypothesis as a necessary but temporary fix for the problems of blackbody radiation, not as a fundamental principle of nature. He did not foresee the full range of applications that quantum mechanics would eventually have, nor could he have predicted how the quantum revolution would unfold. However, his work sparked a chain reaction that would lead to the development of quantum mechanics by figures such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. These scientists would go on to develop the principles of wave-particle duality, the uncertainty principle, and the concept of superposition, all of which would shatter the classical view of a deterministic universe. The impact of Planck's work was not limited to theoretical physics. The advent of quantum theory revolutionized numerous scientific fields and led to the development of technologies that have transformed the modern world. Quantum mechanics has had a profound influence on fields such as electronics, computing, and material science. One of the most significant applications of quantum mechanics has been in the field of semiconductors, which are the backbone of modern electronics. Quantum principles, such as the quantization of energy levels in semiconductors, have enabled the development of transistors, which form the foundation of all modern computing devices. In addition to semiconductors, quantum mechanics has also led to the development of technologies such as lasers, which are used in everything from medical treatments to telecommunications. The advent of quantum computing is perhaps the most exciting potential application of quantum theory, as it promises to revolutionize information processing by harnessing the principles of quantum superposition and entanglement. Quantum computing could potentially solve problems that are currently intractable for classical computers, such as simulating complex molecules for drug discovery or optimizing supply chains. Planck's discovery also had far-reaching philosophical implications. The quantization of energy challenged the deterministic worldview that had dominated classical physics. In classical mechanics, the universe was seen as a giant clock, with every event predictable if we had enough information. Quantum mechanics, however, introduced an inherent uncertainty at the subatomic level, as demonstrated by Heisenberg's uncertainty principle, which states that it is impossible to simultaneously know both the position and momentum of a particle with absolute precision. This uncertainty fundamentally altered our understanding of the nature of reality. Instead of a predictable, deterministic universe, quantum mechanics revealed a probabilistic world, where events could only be described in terms of probabilities rather than certainties. This shift in thinking had profound philosophical implications, raising questions about the nature of reality and the role of the observer in determining outcomes. As the 20th century progressed, quantum theory became increasingly successful in explaining the behavior of the atomic and subatomic worlds. The advent of quantum electrodynamics, QED, and the Standard Model of Particle Physics, which incorporates quantum principles, further solidified the validity of quantum mechanics. Today, quantum mechanics is one of the most successful and experimentally validated theories in the history of science. It is the foundation of modern physics and continues to drive advances in technology and our understanding of the universe. Max Planck's contribution to science was truly revolutionary. His introduction of quantized energy was the spark that ignited the quantum revolution. Although he did not fully grasp the broader implications of his work, his discovery laid the foundation for the development of quantum mechanics and forever changed our understanding of the physical world. Today, Planck's constant **H** is one of the most important constants in all of science, and his work continues to inspire and shape the future of physics. Through his insight, Planck transformed the way we understand energy, light, and matter, and his contributions continue to shape the trajectory of modern science. The emergence of quantum theory and the understanding of quantization principles was not an overnight revolution. It was the work of many brilliant minds building on the foundational discoveries that Max Planck made in the early 20th century. Although Planck's theory initially only applied to black body radiation, the far-reaching implications of his discovery were soon realized by other scientists who extended his ideas to other areas of physics. The true power of Planck's insights became evident when the mathematical framework he established for the emission of radiation was used to explain phenomena in light, matter, and atomic structure. The work of Albert Einstein, Niels Bohr, Werner Heisenberg, and others turned quantum theory from a mathematical model into a radical and new understanding of the physical world. One of the first and most prominent applications of Planck's quantization concept was in the explanation of the photoelectric effect by Albert Einstein in 1905. In the classical view of light, light was understood as a continuous electromagnetic wave. However, experiments conducted by Heinrich Hertz and others had shown that when light was shown on certain metals, it caused electrons to be emitted. The problem was that classical theory predicted that the energy of the ejected electrons should depend on the intensity of the light, not the frequency. In contrast, experiments showed that the energy of the emitted electrons depended only on the frequency of the light and not on its intensity. This contradiction raised serious doubts about the wave theory of light. Einstein, building on Planck's idea of energy quanta, proposed that light itself must be quantized. He suggested that light was made up of discrete packets of energy, which he called asterisk, asterisk, photons, asterisk, asterisk, and that the energy of these photons was directly proportional to the frequency of the light. As Planck had formulated, this explanation perfectly matched the experimental results. The photoelectric effect showed that light, rather than being a continuous wave, exhibited particle-like behavior, supporting Planck's theory of quantization. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921, and it played a crucial role in the development of quantum theory. While Einstein's explanation of the photoelectric effect was groundbreaking, the full scope of Planck's contribution would not be realized until the development of atomic theory in the 1,910 seconds and 1,920 seconds. In 1913, Niels Bohr took Planck's idea of quantization and applied it to the behavior of electrons in atoms. Before Bohr, the structure of atoms had been poorly understood. The electron, as described by classical physics, should have been spiraling into the nucleus due to electromagnetic attraction, which would result in the atom collapsing. However, atoms were stable, and the behavior of light emitted by atoms, such as the distinct spectral lines observed in hydrogen, could not be explained by classical theory. Bohr proposed that electrons in an atom occupy specific quantized energy levels. Electrons could not exist in arbitrary energy states, but instead must reside in one of these discrete levels. When an electron transitioned between these levels, it would emit or absorb radiation at specific frequencies corresponding to the energy difference between the levels. This model, although not entirely accurate by modern standards, successfully explained the observed spectral lines of hydrogen. Bohr's model of the atom was a direct application of Planck's idea of quantized energy and represented a dramatic shift in the understanding of atomic structure. The success of Bohr's model sparked a new wave of research into the behavior of atoms and subatomic particles. However, it also revealed limitations in our understanding of the quantum world. Classical physics had always assumed that particles, such as electrons, followed clear paths or trajectories, much like a ball rolling down a hill. But the behavior of electrons and other subatomic particles was more complicated than that. In 1925, Werner Heisenberg introduced his uncertainty principle, which stated that certain pairs of properties, such as an electron's position and momentum, could not be measured simultaneously with arbitrary precision. The more precisely one property was measured, the less precisely the other could be known. Heisenberg's uncertainty principle was a direct challenge to the deterministic nature of classical mechanics. In classical physics, if you knew the position and velocity of a particle, you could predict its future motion with complete certainty. However, in quantum mechanics, the uncertainty principle showed that the very act of measurement disturbed the system, making it impossible to determine both position and momentum with absolute accuracy. This introduced a new level of indeterminacy into our understanding of the quantum world. In parallel to Heisenberg's work, Erwin Schrödinger, in 1926, developed wave mechanics, a mathematical framework for describing the behavior of quantum particles. Schrödinger's wave equation described how the quantum state of a system evolves over time and provided a way to calculate the probability distribution of a particle's position and other properties. Schrödinger's wave equation was able to explain many phenomena, such as the energy levels in atoms, and it was an important step toward the development of modern quantum mechanics. In this new framework, particles were no longer seen as discrete, point-like objects. They were described by wave functions that represented the probability of finding a particle in a particular state. The development of quantum mechanics reached its maturity in the 1920 seconds, and it became clear that the quantum world was fundamentally different from the classical world. In quantum mechanics, particles could exhibit both wave-like and particle-like behavior, depending on the circumstances. This duality, known as wave-particle duality, was one of the central features of quantum mechanics. The behavior of quantum particles could not be described by classical physics, which viewed particles and waves as distinct entities. Instead, quantum mechanics showed that these properties were interconnected and that particles could display characteristics of both waves and particles in different experimental contexts. The wave-particle duality of quantum mechanics was famously demonstrated in the double-slit experiment, first performed by Thomas Young in 1801 and later adapted for electrons and other particles. In the double-slit experiment, particles, such as electrons, were fired at a screen with two slits, and the resulting pattern was observed on a detector screen. When only one slit was open, the particles created a pattern consistent with particle-like behavior. However, when both slits were open, a wave-like interference pattern emerged, suggesting that the particles were behaving as waves. This result demonstrated that particles could exhibit wave-like behavior under certain conditions, supporting the wave-particle duality of quantum mechanics. The realization that particles could behave like waves led to new concepts in quantum theory. For example, the idea of superposition emerged, which states that a quantum system can exist in multiple states at once, and only upon measurement does it collapse into one particular state. This principle, known as the superposition principle, became a cornerstone of quantum mechanics and was central to the development of quantum computing and other quantum technologies. Superposition challenged classical notions of reality, as it suggested that the act of observation played a crucial role in determining the state of a system. As the 20th century progressed, quantum mechanics continued to develop and expand, leading to the formulation of the Standard Model of particle physics. This model, which describes the fundamental particles and forces that make up the universe, is built on the principles of quantum mechanics. Quantum mechanics has been immensely successful in explaining the behavior of particles and interactions at the subatomic level, and it has been experimentally validated to a degree unmatched by any other theory in physics. The practical applications of quantum mechanics have had a profound impact on technology and society. Quantum mechanics is the foundation of technologies such as transistors, semiconductors, lasers, and magnetic resonance imaging, MRI, all of which have transformed the modern world. The development of quantum computing, which uses the principles of superposition and entanglement, promises to revolutionize fields such as cryptography, optimization, and artificial intelligence. Quantum cryptography, for example, uses quantum principles to create virtually unbreakable encryption, which has significant implications for securing sensitive information. Quantum mechanics has also raised profound philosophical questions about the nature of reality. The probabilistic nature of quantum theory, combined with the uncertainty principle and the wave-particle duality, challenges our classical intuitions about the world. In classical physics, reality was deterministic, and events could be predicted with certainty if we knew the initial conditions. Quantum mechanics, however, suggests that at the quantum level, the future is inherently uncertain and that particles can exist in multiple states at once until observed. This has led to debates about the role of the observer in determining the outcome of quantum experiments and about the nature of reality itself. Max Planck's discovery of energy quantization was the spark that ignited the quantum revolution, and the work of subsequent scientists built upon his ideas to form the framework of quantum mechanics. Quantum theory has transformed our understanding of the universe, and its principles continue to shape the future of science and technology. The development of quantum mechanics has not only changed the way we view the physical world, but has also led to groundbreaking technological advancements that continue to influence every aspect of our lives. Planck's constant **H** remains one of the most important constants in physics, and his work continues to inspire new generations of scientists to explore the strange and fascinating world of quantum physics. Max Planck's groundbreaking introduction of quantization in energy marked the beginning of a revolutionary shift in the understanding of physics. His work on blackbody radiation revealed that energy is not emitted in a continuous fashion, but in discrete packets, which he termed quanta. This was a radical departure from classical physics, where energy was thought to vary smoothly. Planck's quantization idea was initially introduced as a mathematical convenience to solve the ultraviolet catastrophe, a problem within thermodynamics that classical physics could not explain. Although Planck himself did not fully recognize the extent of the revolution he was starting, his discovery laid the foundation for quantum mechanics, a field that would go on to transform our understanding of the universe at the atomic and subatomic levels. Planck's work was a response to a critical challenge in physics, the inability of classical theory to explain the spectrum of radiation emitted by a black body. Classical physics, particularly the Rayleigh-Jeans law, predicted that as the temperature of an object increased, it would emit infinite amounts of energy at short wavelengths, particularly in the ultraviolet range. However, experimental observations showed that the radiation emitted by heated objects peaked at a specific wavelength and then decreased at higher frequencies, which contradicted classical predictions. This discrepancy, known as the ultraviolet catastrophe, was a major gap in classical physics and required a new theoretical approach. Planck's insight that energy could only be emitted in quantized amounts was a novel solution that resolved this paradox and matched experimental observations. His radiation law explained the distribution of energy across various wavelengths and fitted experimental data precisely, providing a breakthrough that would redefine the very nature of energy itself. One of the most significant aspects of Planck's discovery was the introduction of Planck's constant H*70D, a fundamental constant in physics that became central to the development of quantum theory. In his equation, E equals HNIU**, where E** is the energy, H** is Planck's constant, and NIU** is the frequency of radiation. The constant **H** became a fundamental quantity that governs the relationship between energy and frequency. This equation not only solved the black body radiation problem, but also hinted at a broader principle that energy is quantized in discrete units. Planck's constant would later become one of the most important and universally recognized constants in physics, underpinning key equations throughout quantum mechanics. It would go on to influence the development of technologies such as semiconductors and quantum computing, both of which rely on quantum mechanical principles. While Planck's work primarily dealt with radiation, the implications of his discovery extended far beyond black body radiation. His idea of quantized energy opened the door for other physicists to explore the microscopic world of atoms and molecules. One of the first to build upon Planck's ideas was Albert Einstein, who in 1905 used the concept of quantized energy to explain the photoelectric effect. Einstein proposed that light, which had traditionally been understood as a continuous wave, must also behave as discrete packets of energy called photons. This explanation resolved the discrepancies observed in experiments on the photoelectric effect and confirmed Planck's quantization idea in the realm of light. Einstein's work would later be recognized with a Nobel Prize, further validating the importance of Planck's discovery. In addition to Einstein, Niels Bohr applied Planck's idea of quantization to the structure of the atom. Before Bohr, the classical view of the atom was that electrons orbited the nucleus in continuous paths. This posed a problem, as classical physics predicted that the electrons would spiral into the nucleus due to electromagnetic radiation, causing the atom to collapse. Bohr, using the idea of quantized energy levels, proposed that electrons could only occupy discrete orbits around the nucleus. When an electron moved between these orbits, it would absorb or emit energy in discrete amounts, corresponding to the difference in energy between the levels. Bohr's model of the atom was revolutionary because it explained the stability of atoms and the discrete spectral lines emitted by elements like hydrogen. Bohr's work would form the foundation of atomic theory, which was later refined by the development of quantum mechanics. The most profound consequence of Planck's discovery was the shift from a deterministic view of the universe to a probabilistic one. Classical physics operated on the principle of determinism, where the future behavior of an object could be predicted if its current state was known. However, quantum mechanics, which emerged from Planck's quantization ideas, introduced uncertainty and probability into the equation. Werner Heisenberg's uncertainty principle, introduced in 1927, showed that certain pairs of physical properties, like position and momentum, could not be precisely measured at the same time. This principle shattered the classical idea that the universe could be precisely predicted. Instead, quantum mechanics showed that at the microscopic level, particles existed in states of probability, with their behavior governed by statistical rules rather than certainty. This shift in perspective not only revolutionized physics but also had profound implications for philosophy, as it challenged deeply held beliefs about the nature of reality itself. Max Planck's work is considered the spark that ignited the quantum revolution, a revolution that has since transformed science, technology, and our understanding of the universe. Although Planck did not fully grasp the breadth of his discovery, his insights into the quantization of energy set in motion the development of quantum mechanics, which would become one of the most successful and powerful theories in the history of science. Quantum mechanics has had wide-reaching impacts, from the development of technologies like transistors and lasers to advancements in fields like quantum computing and quantum cryptography. The implications of Planck's work continue to unfold as scientists explore new frontiers in quantum science, from the strange world of quantum entanglement to the possibilities of quantum information processing. In conclusion, Planck's contribution to science was not just solving a problem in black-body radiation, but laying the foundation for an entirely new understanding of the natural world. His introduction of quantized energy marked the beginning of a profound shift in physics, leading to the development of quantum mechanics and changing the course of scientific discovery. Today, Planck's constant is a cornerstone of modern physics, and his work continues to influence fields as diverse as material science, quantum computing, and fundamental physics. What began as an attempt to solve a specific theoretical problem became a transformative discovery that altered the way we see the universe, opening up new realms of inquiry and possibility. Max Planck's groundbreaking work in the early 20th century fundamentally altered the trajectory of modern physics. Planck's insight into the quantization of energy emerged from his attempt to solve the black-body radiation problem, a long-standing issue in thermodynamics. At the time, classical physics, which was rooted in continuous energy concepts, could not explain the observed spectrum of radiation emitted by heated objects. When radiation from a black body was studied, classical theories predicted an infinite amount of energy emitted at high frequencies, which contradicted experimental data. This paradox, known as the ultraviolet catastrophe, was a critical gap in the classical understanding of radiation. Planck's revolutionary idea was that energy could not be emitted or absorbed in a continuous manner, as classical physics suggested. Instead, he proposed that energy is quantized, emitted in discrete packets known as quanta. This insight came in the form of his now famous equation **E equals HNIU***, where **E*** is the energy of the quantum, **H*** is Planck's constant, and **NIU** is the frequency of the radiation. By applying this concept to black-body radiation, Planck successfully resolved the ultraviolet catastrophe and provided a mathematical model that accurately described the observed radiation spectra. This marked the first instance in history where the idea of discrete energy units was mathematically formalized. The implications of Planck's work extended far beyond the problem of black-body radiation. His idea of energy quantization had profound consequences for the future of physics. Planck himself, however, did not fully recognize the long-term significance of his discovery. He saw it as a temporary solution to a particular problem and did not envision how it would shape the development of quantum theory. Nonetheless, his work laid the foundation for later breakthroughs in quantum mechanics, a field that would forever change the scientific worldview. In the years that followed, other physicists built on Planck's concept of quantization. Albert Einstein, in 1905, extended Planck's ideas to light, using them to explain the photoelectric effect. Einstein proposed that light is composed of discrete particles called photons, each carrying energy proportional to the frequency of the light, just as Planck had described for radiation. This work earned Einstein the Nobel Prize in Physics in 1921 and was a critical step in the development of quantum theory, solidifying the idea that both energy and light are quantized phenomena. Additionally, Niels Bohr applied Planck's quantization concept to atomic theory. Before Bohr, the classical model of the atom could not explain why electrons did not spiral into the nucleus due to electromagnetic radiation. Bohr's model, which introduced the idea of quantized energy levels for electrons, successfully explained the stability of atoms and the discrete spectra observed in hydrogen. By applying Planck's quantization principle to atomic transitions, Bohr demonstrated that electrons could only occupy specific, quantized orbits, and radiation was emitted when electrons moved between these orbits. Bohr's work, while not perfect, represented a major step forward in atomic theory and further validated Planck's ideas. The development of quantum mechanics, as influenced by Planck's quantization of energy, was not just a theoretical revolution, it also changed the very nature of how scientists viewed the universe. Classical physics was deterministic, meaning that the future state of a system could be predicted with absolute certainty if its current state was known. In contrast, quantum mechanics introduced an inherent uncertainty at the atomic and subatomic levels. This uncertainty, encapsulated in Heisenberg's uncertainty principle, stated that certain pairs of physical properties, such as position and momentum, could not be precisely measured simultaneously. This shift in thinking shattered the deterministic view of the universe and introduced a probabilistic nature to physical laws. Planck's constant H** emerged as one of the fundamental constants of nature. Its significance grew as quantum mechanics developed, becoming central not only to quantum theory but also to the technologies that emerged from it. Quantum theory would eventually give rise to groundbreaking advancements in fields such as semiconductor technology, quantum computing, and communications. The application of Planck's concept of energy quantization continues to have far-reaching effects on modern science and technology, cementing his role as one of the key figures in the scientific revolution of the 20th century. In conclusion, Max Planck's discovery of quantized energy units marked the birth of quantum theory, fundamentally transforming our understanding of energy, matter, and the physical universe. His equation for black-body radiation addressed a critical flaw in classical physics and laid the groundwork for future advancements in quantum mechanics. Through his work, Planck set in motion a series of discoveries that would redefine our conception of reality itself, moving us from a deterministic universe to one governed by probabilities and uncertainties. Today, the legacy of Planck's discovery is felt across science and technology, from the development of modern electronics to the potential future of quantum computing. Max Planck's contribution to the foundation of quantum theory remains one of the most significant milestones in the history of physics. In the late 19th century, physicists were faced with the problem of black-body radiation, a key aspect of thermodynamics that classical physics could not explain. According to classical theory, as an object gets hotter, it should emit increasing amounts of radiation across all frequencies. However, experimental observations showed a different reality. Radiation peaked at a certain frequency and then decreased at higher frequencies, a phenomenon classical theories could not account for. This paradox, known as the ultraviolet catastrophe, prompted the need for a new approach. It was in this context that Max Planck introduced the concept of energy quantization. Planck's solution to the problem was to propose that energy was not emitted or absorbed continuously, but rather in discrete units or quanta. This insight marked the beginning of quantum theory. His equation E equals HNIU where E is the energy of the quantum, H is Planck's constant, and NIU is the frequency of radiation, was a breakthrough that matched experimental data perfectly. This quantization concept resolved the ultraviolet catastrophe and provided a new framework to understand how energy was transferred at the microscopic level. One of the most important elements of Planck's discovery was the introduction of Planck's constant, H**. This constant would go on to become one of the most fundamental quantities in modern physics. In Planck's equation, H** served as the proportionality factor between the frequency of radiation and its energy, demonstrating that energy changes in discrete steps rather than continuously. The constant itself, with a value of approximately **6.626 x 10 to the power of -34 J's, would later be used in many other contexts within quantum mechanics, making it a cornerstone of the theory. Though his work was initially seen as a mathematical convenience, Planck's idea of quantized energy would lay the groundwork for a fundamental shift in physics. While Planck himself saw this as a temporary fix to an existing problem in thermodynamics, his work would eventually provide the foundation for the entire field of quantum mechanics. At the time, classical physics was firmly entrenched in the scientific community, and the idea of discrete energy units was difficult to accept. However, as the implications of Planck's work were realized and extended by other scientists, it became clear that energy quantization was a critical discovery that would change the way scientists understood the natural world. One of the key developments following Planck's work came from Albert Einstein, who extended the idea of quantization to light. In 1905, Einstein explained the photoelectric effect by suggesting that light, traditionally understood as a continuous wave, was in fact made up of discrete packets of energy, which he called photons. Einstein's work confirmed Planck's hypothesis and showed that quantization was not limited to heat radiation, but also applied to electromagnetic waves, further validating Planck's discovery and pushing the boundaries of the theory. Planck's idea of energy quantization also played a critical role in Niels Bohr's development of atomic theory. Bohr applied the concept of quantization to the behavior of electrons in atoms. According to classical physics, electrons should spiral into the nucleus due to electromagnetic radiation, causing atoms to collapse. However, Bohr proposed that electrons could only exist in specific, quantized orbits around the nucleus. When an electron transitioned between these orbits, it would emit or absorb energy in discrete amounts, much like the quantization Planck had described for blackbody radiation. This model of the atom explained the discrete spectral lines observed in hydrogen, marking a significant breakthrough in atomic theory and reinforcing Planck's ideas. The most profound impact of Planck's work was its contribution to the emergence of quantum mechanics, which fundamentally changed how scientists viewed the universe. Classical physics operated under the assumption of determinism, where the future of a system could be predicted if its current state was known. However, quantum mechanics, which emerged from Planck's work, introduced an inherent uncertainty in the behavior of particles at small scales. Werner Heisenberg's uncertainty principle, for example, stated that certain pairs of properties, such as position and momentum, could not be simultaneously measured with arbitrary precision. This shift from determinism to probabilistic outcomes would become a hallmark of quantum mechanics. In conclusion, Max Planck's discovery of energy quantization marked the beginning of a profound shift in physics. His work provided the first successful resolution to the black-body radiation problem and introduced the idea that energy is emitted in discrete units. Though initially seen as a mathematical convenience, Planck's insight set the stage for the development of quantum mechanics, a theory that would fundamentally change our understanding of the universe. Through the work of Planck, Einstein, Bohr, and others, quantum theory emerged as a powerful framework that not only explained previously unexplained phenomena, but also led to technological advancements that have transformed the modern world.